Okay, today we're going to be working what we call applied optimization problems. What we're trying to do here to optimize, we're trying to find maximum points, minimum points. Production-wise, you see this a lot in the industry. You're trying to maximize production. You're trying to pretty much stretch your dollar as far as it'll go. Trying to minimize material that you use. If you're trying to construct something, you want to construct something with the minimum amount of material. You're wanting to get the maximum volume, maximum area, make it as big as possible with as little material as possible. So that's what we're doing today, is you're seeing some of the application problems of all of this calculus stuff. Reminder that maximums and minimums occur. Critical points occur anywhere your derivative is equal to 0, or we know with like this type function, anywhere your derivative could be undefined would be a possible maximum or minimum point. So that's what we're going to do. We're going to try to set up different functions, relationships among what we're given, and we're going to try to find the points of maximum or minimum, really whatever we're looking for. Okay, we're going to start out with an easier problem. Well, we've got a rectangle that has an area of 9, and we want the smallest perimeter possible, or the smallest dimensions possible. First thing on these problems, well, you can start out by drawing pictures just to where you get an idea of what you're looking for. You've got a rectangle with an area of 9. You want to somehow figure out which rectangle is going to have the smallest perimeter possible if it's got this area. We don't know length or width, but we do know that to find area of a rectangle, you have to multiply length times width. So what you're going to do, again, draw a picture to kind of give you an idea, and then try to define. Here's the key point, and you might want to star this, make sure that you know this. Try to use as few of variables as possible. Like here, I'm going to let one of my side lengths be x. Don't let the other side length be y. If at all possible, try to define as much stuff with a single variable. And that's what we're going to do here. Is we've got a side length of x. We've got the other side y. I know in order to you can start out calling it whatever you want to. I'm going to call it w just to show you something, because sometimes I have to do this. I know that when I multiply these two things, x times w, it's going to give me that area that I'm talking about. But I would really, instead of defining this in terms of w, I'd really like to define it with x's. So I can go up here and actually solve this little equation, move the x over, and I know that w is equal to 9 divided by x. So instead of defining this in terms of w, let's try to define it in terms of x. So I've got this rectangle now that's got a side length of x and another side length of 9 divided by x, and you can check that. The area should be 9. If you multiply x times 9 over x, x's cancel, leaves you with 9. So it checks out. So here's my rectangle, and I want to somehow, it says, I want the smallest perimeter possible. I want to somehow minimize perimeter. Well, first off, let's write a function for perimeter. I know that the perimeter is what you get when you add up all four sides. So I have here, this is x, this is also 9 over x. So I have x plus x, which is 2x, plus 9 over x plus 9 over x, which would be 18 over x. You've got common denominators there. We're about to try to minimize or maximize perimeter. So a reminder that maximums and minimums occur of a function anywhere your derivative is equal to 0. Okay, one thing I noticed, we're about to find the derivative of this, so go ahead and take this 18 over x, and let's write this perimeter as 2x plus 18x to the negative 1, which makes it so much easier to find the derivative of. So here we go, we're ready now. We find maximum and minimums anywhere that we have undefined or 0 derivatives, anywhere our slope's equal to 0. Before we do that, though, I should have done this before. We have to be very careful of our domain. The things that x can and can't be, because if we find a maximum, hey, I think I have a maximum at x equals 25 or x equals a million or something like that. We've got to make sure that that's a value that x could possibly be. And I do know this, since x is a side length, the domain, I do know that x has to be greater than 0. It's not greater than or equal to. Now the question is, could x be something like 100? Can I do 9 divided by 100? Sure. If x is 100, then you got 9 100ths, and I guess x could be 1,000,000 here. If x is 1,000,000, then you got 9 divided by 1,000,000, which is a really skinny side, but it's possible. Okay, if this is 1,000,000 and this is 9 over 1,000,000, you multiply the two, you still get an area of 9. So this is my only domain restriction. We've got to make sure that x is a positive number. X can't be -3 because it's a side length. So here, back to it. Minimize perimeter. Let's go ahead and find the derivative. Derivative of 2x is 2. The derivative of 18x to the -1, bring the -1 down front and multiply, is -18x to the -2. We're going to rewrite that as, let's go ahead and put this stuff first, -18 over x squared plus 2. So that's the function that I'm going to try to find a 0 derivative, or anywhere it's undefined, because again, my critical values occur anywhere a function is undefined, which goes to show you also that that's another important reason to do this. I know that my function is undefined at 0, but it's not a critical value because x can't be 0. Okay, I'm not going to have a maximum or minimum at 0 because x can't be it. All values of x has to be bigger than 0. You plug in a 0 here and nothing happens. You've got an undefined function. So we don't have anywhere where the function is undefined because of our domain. But we will have places where my function is equal to 0. That's where we're looking to solve now. That's going to be my critical value. Set it up equal to, derivatives equal to 0. Let's move our 2 over and our x squared at the same time. I got -18 equals, when the 2 comes over it becomes -2. I'll end up multiplying by x squared. That'll be -2x squared. Divide now by -2 and you get 9 as x squared. Square root both sides, you get x is, you don't have to worry about positive -3 again because of this. X is 3. That's my critical value. X equals 3. Now, most of the ones that they're going to give you, and I'm going to do it here, most of the ones that they're going to give you, they're going to use what we used last section. This is a critical value. Something's happening here. I want to see, is this possibly a maximum or a minimum here? And here's how you do it. Go ahead and find the second derivative. You could look at the graph and do this exact same thing. The way we're going to do it today, we're going to find the second derivative. Let's take it from here. The derivative of 2 is 0. The derivative of -18, x to the -2, bring down the -2, gives you 36x to the -3, which is 36 over x to the third. There's your second derivative. Here's the only reason I have to find the second derivative. Plug the critical value in. You get 36 over 27, which is a positive number. What that tells you is, reminder, a second derivative tells you concavity. It tells you whether your function is concave down or whether it's concave up. If you get a positive value, it's concave up. If you get a negative value there, it's concave down. So at your value, at your possible critical value of x equals 3, you have a function which is concave up at that value, which is a critical value. And if it's concave up at a critical value, that must mean that you have a minimum at that critical value, which is what we were looking for. So at x equals 3, which we go back to our original drawing, I like to do this. When x is 3, you have 3 here, and you have 9 divided by 3, which is also 3 here. You've just minimized the perimeter. They're also going to ask you on your homework, find the value of a side that minimizes the perimeter, and then actually find the perimeter. What's the smallest perimeter that this area of 9 could have? That'd be, this is 3, so the perimeter would be 12. So the side length that minimizes, and you can try different ones now. You can try, well, what if this was 2 and this was 2? You'd have 2 and 2 is 4, that'd be 4.5 and 4.5, which is 9. 4 and 9 is 13. That's a little bit bigger. This is the smallest perimeter that you can possibly have if you have an area of 9. Okay, on the next one, it says, find the dimensions of an open rectangular box of maximum volume that can be made from a sheet of cardboard that's 13 inches by 8 inches by cutting congruent squares from the corners. So see if you can picture this. We're going to cut little bitty squares, congruent, same size, has to be in order to do this. We're going to cut little squares out of the corners of this rectangular piece of cardboard. We don't know how big they are, but since they are squares, they'll be X by X squares. Once we cut these off, we're going to fold this up, we're going to fold this up, all the way around. It's going to form a box, okay, a rectangular prism. And we want to know how big of corners should we cut out to where when we fold this box up, we get the biggest box possible. And again, you see, when I first started out, we're talking about manufacturing, why this would be valuable. Why would this be something good to know? We want the box that's going to hold the most amount of material. Or if we're a cereal company, obviously we want the box that will hold the least amount of cereal, but it looks like it's going to hold the most. To where they're going to get about 2 bowls of cereal out of it, and then they're going to have to go back to Walmart buying of it. So here we go. Here's how we're going to do it. First off, let's figure out what the volume of this box is, and see if this makes sense. If the whole side is 13, if you can try to picture the box after, let me see if I can draw it. The box after you cut those corners out, it's going to look kind of like this. Okay, you've cut this out here. You folded this up for a side. That side is no longer 13. Okay, because you cut out whatever this length is and whatever this length is, and that's going to be the length of whatever this side is, which would be the full 13 that you had before, but you cut out an X here and you cut out an X here. So the width of this side is going to be 13 minus 2X. The width of this side, well, it was 8 until you cut these little chunks out, and now this is all you're folding up for a side, is just this portion. So you cut an X out here and an X out here, the width of this side will be 8 minus 2X. And then once you fold it up, the height of your box, anybody know what that is? The height will be X. So this is 13 minus 2X, this is 8 minus 2X, and the height of the box is X. We want to maximize volume. We want the volume that's going to be largest. How big of an X do we need to maximize volume? So first off, let's actually find a formula for volume. Length times width times height, or the area of the base times the height. So that'd be X times 8 minus 2X times 13 minus 2X. That's the formula for volume. And here's my thing. You can leave it like it is and then find the derivative, because we want to find where's the highest volume. If you leave it like it is and find the derivative of this, you're going to have to use the product rule twice in the same problem. It's going to be terrible. My suggestion, use your basic algebra and go ahead and FOIL that out. It's going to make the problem much easier, because you're going to end up with just like a polynomial. So let's go ahead and do that. So volume is equal to, leave the X. It's going to be easy to just distribute that at the end. You have 8 times 13, which is 104, 8 times negative 2, which is negative 16X, negative 2X times 13, which is a negative 26X, and negative 2 and negative 2, which is a positive 4X squared. Next, I'm going to distribute that X, and as I do that, this is negative 42X. As I distribute the X, I'm actually going to put these in order as well. I'm going to put my 4X squared first. X times 4X squared will be 4X to the third. Negative 42X times X will be negative 42X squared, and 104 times X will be plus 104X. So here's my formula for volume. That's what I'm trying to maximize. I'm trying to figure out what is the largest value of X that I could possibly have. Something I also forgot how to do. Something else I forgot to do is I need to define my domain restrictions. What are some values that X could be, and what can X not be? Let's point out that obviously X can't be negative, because how in the world can you have a negative height? X can't be 0. You can't have a 0 height. So let's say that X must be positive, or has to be greater than 0, and has to be less than. Okay, look at here. If x were 4 here, 8 minus 8 is 0. That'd mean you'd have a 0 width. So there's no way possible that x could be 4. There's no way, well, here x can't be 6.5, but that's not going to come into play as long as we fix this. So x has to be somewhere between 0 and 4, not including 0, not including 4. That's my domain. That's the only values. That's the short interval where I've got to try to find a maximum volume here. Is somewhere between 0 and 4. So what is the maximum volume that I could occur, or that can occur in this height here? Let's find out. So in order to find that maximum, again, find v prime. And it's a simple polynomial now. Move the 3 down front, multiply, take 1 away. Same thing here, negative 84x. And 1 times 104 is a positive 104. So there's your v prime. Anywhere it's undefined or anywhere it's 0 is where your critical values occur. This cannot be undefined. There's no value that it's no fractions, there's no square roots, there's no tangents, there's no anything like that to force undefined here. So all we're working